Welcome everyone. The topic for today is the symmetric group. The symmetric group is one of the most important examples of groups for reasons that hopefully will become clear during the talk. So what is a symmetric group? So let's fix a positive integer n, and then the symmetric group on n letters is the group consisting of all bijections from the set 1, 2, all the way through n back to itself. Bijections on a finite set are the same thing as permutations. So in other words, these are all the permutations of the set 1 through n. And to give you a group, I not only have to give you the set, I also have to give you the operation. And the operation is just composition of functions. A bijection is a function from this set to itself, so it makes sense to compose them. You already know that composition of functions is always associative, so you just need to check that there exists the identity element and that every element has an inverse. Now clearly, the identity permutation will be the permutation that does nothing, so it doesn't permute anything. So I'll denote this by E. So here, E will be the do-nothing permutation. i.e., E sends any element, any integer, from 1 to n, any integer I, back to itself. And secondly, you have to know that every element has an inverse, but clearly if I apply permutation to some finite set, then I can undo this permutation, so I can permute these elements back. In other words, use the inverse function so I get the inverse to that element under our operation, which is composition. Okay, so the symmetric group is denoted by Sn, and note this sort of slightly strange terminology here. It's called the symmetric group on n letters, while I'm using numbers rather than letters. It's just much more convenient to use numbers than to use letters, but I'm not going to dispute the historical terminology of this being called group on n letters. One combinatorial fact before we move on: how many permutations are there of an n-element set, n factorial? So in particular, these groups get pretty big as you increase n. The trivial group can be thought of as S1. So you just have one number 1, and there is nothing to permute, so the only permutation of a one-element set is the identity. And then if you have two elements, there are two things you can do to them. You can either do nothing, or you can just exchange these two elements. So you have 1 and 2. You can either send 1 to 1 and 2 to 2, that's the identity permutation, or you can send 1 to 2 and 2 to 1. So that's the only other permutation you can have, so you have two elements. But as you increase n, you see there are already 6 permutations of a 3-element set, 24 permutations of a 4-element set, 120 permutations of a 5-element set, 720 permutations of a 6-element set, and that's how far my knowledge of factorials goes. So I don't really know what's 7 factorial. But in any case, even if you just have a few numbers, the number of permutations is actually quite big, but always finite. As long as the set is finite, so we always go from 1 to n, so it's a finite set, then Sn will be finite. All right, let's look at an example here. So let's take S5. So that means every element is a permutation of 5 numbers, 1 through 5. In other words, the function from this set to that set, that is a bijection. So here I drew an example of such a bijection, right? This is an example of a bijection, a particular bijection. What does this bijection do? Let's actually read it off this diagram and write it there. So I'm going to write what's sigma of 1. Okay, so 1 is sent to 3. So sigma of 1 is 3. What's sigma of 2? 2 goes to 5. So sigma of 2 is 5. 3 is sent to 4. So sigma of 3 is 4. 4 is sent to 1. 4 is sent to 1. 4 is sent to 4. 4 is sent to 1. 4 is sent to 4. 4 is sent to 1. 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 4 is sent to sigma of 4 is 1. And finally 5 is sent to 2, so sigma of 5 is 2. This is just an example. This is one of the 120 possible permutations of this set. So here I drew it this way. It's a very visual way to represent permutations. It's not the most economical way. You see, it actually took me a long time to do this, so that's why I prepared it ahead of time. And I did something else here that might not be clear at the moment why I did it. Namely, I sort of color-coded this permutation. Why are some elements in orange and some elements in blue? So if you see what happens to 1, 1 is mapped to 3. And then I see what's happening to 3. Well, 3 is mapped to 4. And then I see what's happening to 4, and 4 is mapped back to 1. So this permutation, when you start with 1, and you apply it over and over again, can never get you to 2, and can never get you to 5. It sort of only cycles between 1, 3, and 4. So 1 goes to 3, 3 goes to 4, 4 goes to 1. On the other hand, if you look at 2 and 5, then it sends 2 to 5, and 5 to 2. If I applied it again, then again 2 goes to 5, apply it again, 5 goes to 2. So it also cycles between these two elements. So here on this next picture, I just reordered the elements, right? It's just a set, so I can reorder elements the way I like. So sort of separate the orange ones from the blue ones. And now you see that the permutation just permutes things among the orange subset, and then permutes also things about the blue subset, but it doesn't mix them. So these two sort of pieces of that permutation are called cycles, because you see, there's another way to even think about it, right? So on my permutation, sigma cycles through the elements 1, 3, and 4. 1 goes to 3, 3 goes to 4, 4 goes to 1. And sort of you're back to this. And here, same with 2 and 5, right? It sort of cycles between these two. So there is even a special notation, which is then a very economical notation for permutations. Namely this cycle here, so this is a cycle of length 3, because it's got 3 elements. It's denoted by, okay, I start with the, usually, it is not necessary, but usually to keep some sort of organization, you start with the lowest number, so that's 1, and then you write 3, you follow the arrows, write 4, okay, and end it there. While this cycle here, this is a cycle of length 2, can be written as 2, 5. Okay, and sometimes people even, so nobody really writes these things. People always write just these things. So you read it usually like 1 goes to 3, 3 goes to 4, 4 goes to 1. You see, I don't write 1 again at the end. I just know that the last number always goes to the first one, right? 1 goes to 3, 3 goes to 4, 4 goes to 1. That's what it means. And this means 2 goes to 5, 5 goes to 2. So in other words, what I have done is I have written my permutation, sigma, as a product of these two cycles, as a composition of these two cycles. What am I talking about? This cycle over here and this cycle over here, they can be thought of as completely independent permutations. So I'm going to call, just for the moment, okay, this thing by sigma 1, and this thing I'm going to denote as sigma 2. And see, I can think of sigma 1 does the following. It sends 1 to 3, 3 to 4, 4 to 1, and it doesn't do anything to 2 and 5. So it sends 2 and 5 back to themselves. On the other hand, sigma 2 doesn't do anything to 1, 3, and 4, but it sends 2 to 5 and 5 to 2. So, if I look at my permutation sigma, then that's the same as composing sigma 1 and sigma 2. Because I can just as well first switch 2 and 5 and not do anything to 1, 3, and 4, and then do the mumbo jumbo with the 1, 3, and 4 and not do anything to 2 and 5. So, but of course we have better notation for the sigma 2 and sigma 1. Sigma 2 is just 2, 5, and sigma 1 is 1, 3, 4. Okay? And one usually doesn't write the circle between them. It's sort of understood that that's what goes between two cycles. So a cycle is a permutation like this that sort of permutes cyclically certain elements and leaves the other ones unchanged. So let's talk a little bit more about these cycles, because they're just a very convenient way to write permutations. So you see, one thing here about these two cycles is that they do not share any numbers among them. This one only has 1, 3, and 4. This one has 2 and 5. They don't overlap. Such cycles are called disjoint. So two cycles are called disjoint if they do not share any elements. Let's just say if they do not have any elements in common. And an immediate fact about disjoint cycles is that they commute. Two disjoint cycles can be composed in any order, or let's just say commute. I.e., if I compose them in any order, I get the same permutation. Okay, you see, it's immediately clear, for example, from this situation, that I could have first sent 1 to 3, 3 to 4, 4 to 1, and not do anything to 2 and 5, and then switch 2 and 5. Or I could have first switched 2 and 5, and then do these things to 1, 3, 4. Altogether, I get the same permutation, this one here. Right? So that's a good thing about disjoint cycles, that you can compose them in any order. Another thing about cycles, disjoint cycles, is that any permutation can be written as a product of disjoint cycles. So that is another fact. Any permutation can be written as a product of disjoint cycles. And rather than engage in a formal proof of this statement, let me show you an example and explain how the general statement then can be proven from this example. The only difference between the example and the proof of the statement is that you do not look at particular numbers, you just call these elements a1, a2 through, say, an, and you just have to sort of keep track of the indices. But the idea is completely the same as in the example I'm going to show you. Okay, so let's do a... let's maybe write down here a certain permutation. So, example. Okay, so it's going to be, I wanted to make it somewhat complicated, so there's going to be lots of these numbers. 1 goes to 7, 2 goes to 4, 3 goes to 3, 4 goes to 9, 5 goes to 6, 6 goes to 5, 7 goes to 8, 8 goes to 1, 9 goes to 11, 10 goes to 2, and 11 goes to 10. Okay, so that's my sigma. My sigma then is clearly an element of S11. So it permutes the numbers 1 through 11. Let's make sure that this is actually a permutation. So here, of course, on the left, I have every number represented. Let's make sure that I have, that the image is actually, so that the map is surjective, that I get every element in the image. I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay, so this really is a permutation. So let's try to write it down as a product of the disjoint cycles. So sigma is equal to. How do you do this? I mean, there are several ways to do it, but to keep sort of organized, you can sort of first open parentheses, so for the first cycle, and you start with the lowest number that isn't fixed. Well, let's see. So what's the lowest number? 1. 1. Is it fixed? No, 1 is moved to 7. So I write 1 here, and then I write where 1 gets moved, so 7. Okay? So here I'm going to still do like the picture of the cycle. But you should really start thinking about them in this way rather than in that way. So what happens to 7? Oh, so 7 goes to 8. So I write 8 here. What happens to 8? Oh, 8 goes back to 1. So maybe this picture is too big. 8. And then 8 goes back to 1, so I don't write any more 1. I just close the parentheses. Alright, for the next cycle, I am going to use the lowest number that hasn't been used in the first cycle that isn't fixed. What's the lowest number that hasn't been used in the first cycle? 2. Is 2 fixed? No. Okay, so I can start with 2. So I'm going to use a different color here, so 2. So I start over here at 2. Right? Where is 2 mapped? 2 goes to 4. So I write 4. 4 then goes to 9. Where does 9 go? 9 goes to 11. Okay, I'm going to write 11 here. I don't want to use... Yeah, well, I don't want you to think that it's at 2 1s. I'm just going to write 11 really thinly, like that. So that's 11. Where is 11 mapped to? Oh, 11 goes to 10. That's a long cycle. 10 goes to 2. Oh, 10 goes to 2, so we're back. Okay, so I close the parentheses here. Alright, am I done? I don't know, I don't think so. What am I doing third? I'm looking for the smallest element, the smallest number that does not appear anywhere before and isn't fixed. 3. Is 3 anywhere? No, 3 isn't anywhere. So 3. Oh, but 3 is fixed. See, I could write just that. That would represent 3 going back to itself. But because we're trying to be economical here, we're not going to do this. So we just omit all the elements that are fixed. So if you see a permutation written as a product of disjoint cycles and you see something omitted, that means that thing is fixed. Not that I forgot about it. It just means that that thing is fixed. So I'm not going to write 3 here. What's the next number? 4. Oh, 4 is already used. What about 5? Yeah, 5 hasn't been used. So let's open up another one with 5. 5. What happens to 5? Well, 5 is mapped to 6. What about 6? Oh, 6 is mapped back to 5. So that closes this cycle. What's left? 7 is there, 8 is there, 9 is there, 10 is there, and 11 is there. So this is already the complete cycle decomposition. And note that these cycles here are disjoint, and that is entirely clear because that's how I came up with the cycle decomposition, right? I was starting the next cycle with a number that hasn't yet appeared anywhere, and so like I started here with 2 because 2 wasn't here. And how do I know that 2 is not going to be mapped to one of these numbers so that suddenly these numbers will appear here? Well, I wouldn't. I would know that, right? Because permutation is a bijection. So because 1 is already mapped to 7, 2 is not going to be mapped to 7. 7 is already mapped to 8, so 2 is not going to be mapped to 8. And 8 is mapped to 1, so 2 is not going to be mapped to 1. So I know that none of these elements will appear in this cycle, and so on. So the proof of this fact that any permutation can be written as a product of disjoint cycles goes exactly the same as this example here. Okay, in the next video we'll see how we can compose permutations written in cycle notation.